Welcome to Mr. Swords' science class. Today we're going to be talking about what is a force and how do I calculate it. So first of all, I want to review some things. We're going to talk about Newton's first law in a moment. Newton's first law is that an object at rest will remain at rest and an object in motion will remain in motion unless a force is acted upon it. So this idea here is that this kicker here was standing at rest after he kicked the ball, and then, he was acted upon by an unbalanced force, this guy right here. So he's on the ground. So he ended up moving. He was in motion. And so that's Newton's first law. The idea is that in inertia, things that are sitting will stay sitting. Things that are moving will stay moving unless a force acts upon it. But if there's a force, how do we know how it's going to move? What does this term unbalanced mean? I don't know, but we're going to take a look at it. So let's illustrate that point by looking at Newton's second law of constant acceleration. When an unbalanced force acts upon an object, its force can be described in two ways. First, I'm going to talk about football here because we have the Super Bowl over the weekend. Its mass is inversely proportional to its acceleration. Inversely means opposite. So if mass goes up, acceleration goes down. And if the opposite holds true, if mass goes down, acceleration goes up. And so I'm using football as an example here. If we look here, this lineman here has a lot of mass, and so he's not going to accelerate as fast as Russell Wilson, who has a smaller mass, and so he's going to accelerate a lot more quickly. Now, we know that usually this is objects that are not always trained to be athletic machines, but in this case, I think it holds true. Usually we're talking about just inanimate objects. More mass, it will not accelerate as quickly as those with less mass. That's the idea of inversely proportional. And so when mass goes up, I'm going to do a capital M, acceleration goes down. That's a lowercase a. But if mass is low, acceleration goes up. And that is if the force remains constant. I must remember that as well. If the force is the same that's applied, then this happens. And so Newton's second part is that its acceleration is directly proportional to the force that's applied. And so if I put a little bit of force on a golf ball, it's not going to go as fast. So that's what I do when I putt. But when I drive the ball with a driver club, and I'm putting a lot of force into it, I'm knocking it out of the park. Same mass gets a lot of acceleration. Must remember that mass is constant. On the same object, more force equals more acceleration. Directly proportional. When one goes up, so does the other. When one goes down, so does the other. So they're equally directly proportional. So now that we looked at Newton's three laws, let's take a look at your notes. A force is a push or a pull. And so we have some examples here. We have a guy running. We have a balloon that was popped. We have a pitcher that's throwing a baseball. And we also have a wakeboarder that's flying in the air because of his inertia and his momentum being forced out. We need to remember that there are two things to a force. Not just that it's a push or a pull, but that there's a certain magnitude. Isn't that an awesome word, magnitude? Sounds like some Roman gladiator. A magnitude means strength, how strong the force is. Okay, so if you put a little bit of force in, it's not going to have a lot of magnitude, as opposed to a lot of force. There's a lot of magnitude. And then also, the direction is also a part of it. This force is called a vector quantity, which means vectors involve direction. So you're going to see usually an arrow or a direction that is with that force. So since there's many forces, motion is created. And all these forces are either balanced or unbalanced. When they're unbalanced, we show them as a net force of magnitude and direction. Okay, forces are always measured in newtons. So named after some person, Sir Isaac Newton, maybe? It's a big N, big capital N for that. And our formula that we use to calculate force is force equals mass times acceleration, m times a. And so we look here, we have a mass of 2,000 kilograms. Force will always be measuring using the mass of kilogram units. Kilos is 1,000 grams. And then we're going to have acceleration, 0.5 meters per second squared west. I'm going to talk about that in a little bit later. But forces can act in several different ways. They can act by pushing, pulling, speeding up, slowing down, changing direction, or changing shape. They can smash. They can also stretch. Okay, so lots of different things. So in your work example, we have Fred. Hey, Fred. He's running at a rate of 4 meters per second. He has a mass of 50 kilograms, and so we need to show our work. It's in your example there, but I'm going to walk you through it. We always need to show our formula. Force equals mass times acceleration. I know some of you guys don't like doing that, but at the same time, it helps stay organized, and we need to do this. So we're going to put our mass of 50 kilograms. We know it's our mass because it's got kilograms. That's our little hint. 50 times our acceleration of 4 meters per second. That means every second I'm increasing my speed by 4 meters per second. And so we have 50 times 4. That gets us 200 for our force. And we use the Newton force, N, 200 N. So his force was a rate of 200 newtons. Wonderful. Let's go over these examples. A car weighing 1,000 kilograms was traveling at a rate of 20 meters per second every second. How many newtons of force was that car traveling? What's our formula again? Oh, I got it. Force equals mass times acceleration. Which one is my mass? I'm going to use my unit to help me. Kilograms or meters per second. If you chose 1,000, you're correct! Wonderful. You're great. And 20 is our acceleration. We're accelerating 20 meters per second. So I add or multiply those together, and I get 20,000 newtons for N.